The chain rule can be used to provide a generalized rule for differentiation for our elementary or common functions that we deal with. So all of these generalized derivatives explore the idea of using the chain rule, which says we simply differentiate the outer function. So e to the power of f of x, e to the something is the outer function, and it differentiates to e to the something. And we keep the inner function f of x the same, and then just multiply by the inner function f's derivative. The same applies for log, so we differentiate the outer with the inner still the same, so we get 1 on f, and then we multiply by the derivative of the inner, f dashed of x, and that gives us the generalized rule f dashed of x over f of x. The same applies for sine, cosine, and tangent, where we differentiate the outer function, so sine goes to cos with f of x still in it, and then f dashed of x is multiplied by that, so we multiply by the derivative of the inner. And you can see there cos and tan following those same patterns. So the idea of this example is to determine the derivative for each of the following with respect to x by using almost those shortcuts, or remembering that process of differentiating the outer and then multiplying by the derivative of the inner. So for this question, f of x equals e to the power of sine x. The derivative, f dashed of x, we're going to multiply by the derivative of the inner, so sine of x goes to cos of x, and then we simply differentiate the outer, and e to the something differentiates to e to the something, so we get cos of x times e to the power of, and the sine of x stays there. So that is the answer to part A. So for part B, we have g of x equals log e of cos of 2x. And we simply want to calculate the derivative of this, so we have g dashed of x is equal to, and we're going to derive the inside, so cos of 2x's derivative is negative 2 sine of 2x, and then we divide by just cos of 2x, the original function inside the log. So that gives us the derivative g dashed of x is minus 2 sine of 2x over cos of 2x. However, we know that tan of theta is simply the ratio of sine of theta divided by cos of theta. So therefore our derivative here, g dashed of x, can actually be expressed as minus 2, and sine of 2x on cos of 2x can be written as tan of 2x. So that is the answer for part B of this example. For part C, we have h of x is equal to cos of the square root of x, and that means that h of x could be written as cos of x to the power of a half. And following the process for generalizing the derivative, we take the derivative of the inner, so we take the power out the front, so a half x to the power of, and 1 off the power gives negative a half, and then the derivative of cos is going to be negative sine, and we keep the original function in there. So therefore the derivative h dashed of x is equal to, and here we have a half times x to the power of negative a half. The negative would put the x term on the bottom of a fraction, and the half would have a square root sign there. So this could be written as 1 over 2 times the square root of x. And then we have negative sine of x to the power of a half. So we could have this as just being negative sine of the square root of x. And if you really wanted for that question, you could have h dashed of x is equal to, and you could put sine of the square root of x on the top line, and you'd have negative sine of the square root of x divided by 2 times the square root of x. So one of those three options would all have been acceptable answers for the derivative of cos of the square root of x. And finally for part D, we have y equals tan of 2x squared minus 3x. So the derivative dy dx is going to equal, and we start by differentiating the inner, so that becomes 4x subtract 3, and then we differentiate the outer, which is tan of x, so we could write that as sec squared, with the inner staying the same, which would be 2x squared minus 3x. So that is an answer for D, but you may remember that for differentiation of tan, there is a second way that we can express it. So the derivative dy dx could also have been written as, and we know sec squared is the same as 1 on cos squared, and that's written in the formula sheet. So we could leave the 4x subtract 3 on the top line, and then we divide that by cos squared of the inner 2x squared minus 3x. So that is another equally valid way that we could have expressed this derivative for part D.